Hi, I'm Shin Yen. I am the Algebra 1 Honors and AP Calculus BC instructor for Blue Tent Online. This is a sample lesson for the Calculus BC class. We are currently on Zoom, which is the video conferencing platform that we will be using for this class. Students in the AP Calculus BC class will be able to access live lessons twice a week, where in addition to the lectures, they will be able to ask questions and get their answers. And also they will be able to learn from their classmates' questions and answers. This way, even though this is an online class and we're meeting virtually, the students will be able to interact with me as well as with their classmates. In this video, I will work on an optimization problem, which is a type of application problem that the students in Calc BC will work on after the unit on derivatives. I also chose this problem because it illustrates the type of algebraic skills that will be required of the Calc BC student. So, in an optimization problem, we are usually asked to find either the maximum or the minimum of a function. In this particular problem that I have prepared, we are looking for the minimum length of a wire. So let me read the problem. There are two posts. One is 12 feet high and the other is 28 feet high, and they stand 30 feet apart. They are to be stayed by two wires attached to a single stake, and the wires run from ground level to the top of each post. The question is asked, where should the stake be placed to use the least amount of wire? So this is the position of the stake. So to start our problem, we are going to label our variables and set up our situation. So since the length of the wire is the sum of the two green segments, we are going to call the length of the shorter green segment Y and the length of the longer green segment Z. So you can see that this sets us up very nicely for two right triangles. Here's my first right triangle and here's my second right triangle. And the length of the legs are X. And since the distance from the first post to the second post is 30 feet, if the distance from the first post to the position of the stake is X, then this second length will be 30 minus X. Okay, now let's set up the equations for our two triangles. First, let us write the equation of the length of the wire as a function X, where X is the position of the stake from the first post. So W as a function of X will be equal to Y plus Z, where Y is the hypotenuse of our first triangle and Z is the hypotenuse of our second triangle. So let's set up our Pythagorean triangle. We have that Y squared is equal to X squared plus 12 squared, which gives us Y is equal to the square root of X squared plus 12 squared. So this is our first expression for Y. Now let's find the expression for Z. We have that Z squared is equal to 30 minus X squared plus 28 squared. So that gives us an expression for Z, which is equal to the square root of 30 minus X squared plus 28 squared. All right, so now that we have an expression for Y and we have an expression for Z, we can write the length of the wire as a function of X. That gives us the length of the wire as a function of X is the square root of X squared plus 12 squared plus the square root of 30 minus X squared plus 28 squared. Okay, now we are looking to minimize the length of the wire, and the length of the wire depends on where we put our post. So this is the problem, and this is the equation that we are trying to optimize. Okay. So remember earlier I said that we are usually trying to minimize or maximize a function. This is the function that we are trying to minimize. We would like to ask the question, how does the length of the wire W vary with respect to X? So in calculus, we take the derivative, which allows us to investigate the changes in Wx with respect to changes in X. So let's rewrite our equation. Wx is equal to the square root of x squared plus 12 squared, plus the square root of 30 minus x plus 28 squared. Now we want to take the derivative of this function with respect to x. So let's apply our derivative rules. First, we apply the power rule, which gives us 1/2 x squared plus 12 squared raised to the power of negative 1/2. We apply chain rule to the expression inside the parenthesis, and this gives us 2x. We are going to apply the power rule to the second term, which gives us 1/2 parenthesis 30 minus x squared plus 28 squared raised to the power of negative half. Now we're going to apply chain rule to the expression inside the parenthesis, which gives us 2 times 30 minus x. And we have one additional chain rule, which gives us the term negative 1. We're taking the derivative of 30 minus x. Okay. Now we're going to rewrite this expression, but first we are going to see if there's anything that we can do to simplify it. We notice that the 2 cancels out and the 2's in here cancel out. So let's regroup. We have x over the square root of x squared plus 12 squared plus 30 minus x over the square root of 30 minus x squared plus 28 squared. Let's not forget our term, negative 1. So now we have an expression for the derivative of the length of the wire with respect to x. Now, in order to find the maximum and minimum of this function, we are going to set this equation equal to 0. The values at which the derivative of the function is equal to 0 are the critical points of the equation, and those are the locations where there are possible local minimum and maximum. Okay, so we are done pretty much with the calculus that is involved in this problem. You'll see that previous to this particular portion where we took the derivative, we are setting up, and the setup is very much algebra based. And now that we have taken the derivative, we go back to algebra. So as we work through examples like this in class, we will be reviewing algebraic techniques, and I will be pointing out potential problems and what to look out for as you solve problems of this type. So let's go. Now we set this equal to 0. So in order to solve for x, we are going to move the second term over to the right. So let's rewrite this as x over the square root of x squared plus 12 squared. Here's a minus sign, so when we move this term to the right-hand side, this becomes positive. So we have 30 minus x over the square root of 30 minus x squared plus 28 squared. Okay, now we cross multiply to get x times the square root of 30 minus x squared plus 28 squared, and this equals 30 minus x times the square root of x squared plus 12 squared. Okay, So at this point, we have cross multiplied. And now we are going to square both sides of the equation. And this gives us x squared times 30 minus x squared plus 28 squared. And on the right-hand side, we have 30 minus x squared times x squared plus 12 squared. All right, now our next step is we are going to distribute our factors and write the entire expression out so that we can collect like terms. So we're going to distribute and collect like terms. Okay, so when we do that, we get x to the fourth power minus 30 x to the third power plus 1,684x squared, and this equals to x to the fourth power minus 60 x to the third power plus 1044 x squared minus 8,640x plus 129,600. Okay, these are really big numbers. And the point of working on this problem is to not be intimidated by complex expressions because you'll be seeing a lot of those. But watch what happens. Many terms cancel out and we go from a fourth order equation to a second order expression, which we are very familiar with. All right, so now let me collect like terms and let's move everything to the left-hand side. So we end up with 640 x squared plus 8640x minus 129,600. This is equal to 0. All right, now we end up with a quadratic equation, which we know very well how to solve. So when you have a quadratic equation with big numbers, before you even attempt to factor it, I will recommend that you simplify it as much as you can by factoring out any common terms that you notice. So in this expression, we can factor out 320, and that leaves us with 2x squared plus 27x minus 405. Now we set this equal to 0, and we can now factor this expression, this quadratic equation, which is much easier to solve than the one up here. So now we factor it, and we end up with 2x plus 45 and x minus 9, and this is equal to 0. So this gives us two possibilities for x. X is equal to 9, or x is equal to minus 22.5. Okay, so since x is a positive distance from the 12-foot pole, the number x is equal to 22.5 is going to be an extraneous solution. All right, so this is going to be our local minimum. But the question, if we go back up, is asking us for a global minimum. In order to do that, in order to find the global minimum, we want to check the value of the length of the wire at our extreme points, at our endpoints. And our endpoints are at the left end, we have when x is equal to 0. What happens when x is equal to 0? When x is equal to 0, that means that our stake is at the base of the 12-foot pole, which means that our big triangle is going to be the one formed by the 30-foot distance between the two posts. the 28-foot height, and this is our hypotenuse. And if we solve for this by substituting x into this equation, we have that x is equal to, W is equal to 53.04 feet. Now, if we evaluate W at x is equal to 9, then we have that the distance between the stake and the 12-foot post is 9 feet. So we have this length and this other length, both of them are hypotenuse. And if we solve for the length of the wire when W is equal to 9, we have that that is equal to 50 feet. All right. So our last possibility is the endpoint, the other endpoint, which is when x is equal to 30. That means that the post that at the length of our wire, the stake is at the foot of the 28-foot post. So this becomes the length of the wire, the hypotenuse of the triangle formed by the 12-foot pole, the 30 feet distance between the two posts, and our hypotenuse. So this is W at 9, and this is W at 30. And this distance is equal to about 60 feet. Let's see. It is 60.31 feet. So now we can say for sure that when the stake is placed 9 feet from the 12-foot post, that gives us a minimum length of the wire, which is 50 feet.
Whenever relevant, I will discuss uses of the TI Nspire Calculator. The TI Nspire CAS is a very powerful calculator that is allowed on all the AP and SAT tests, and I strongly recommend getting this calculator and using it throughout the Calc BC class. We start here at the home screen, and I will use the graphing capabilities to show that the length of the wire has indeed a minimum at x is equal to 9. So here is the icon for graphing, and which is the function that is going to represent our function W, which is the length of the wire as a function of the position x of the stake. So that expression is the square root of x squared plus 12 squared plus the square root of 30 minus x quantity squared plus 28 squared. Okay. So we've graphed it, but the graph is actually outside the area of our screen. So we can go to menu. We are going to choose the option 4 to zoom out. So this magnifying glass is asking us where is the center from which we are going to zoom out. So we keep clicking until we see our graph, and there it is. So to get out of the zooming function, we go back to the calculator and we hit escape. Okay. Now I can actually move the graph. Let's see. I'm going to move this. So this is the graph of the length of the wire as a function of the position of the stake. So clearly it has a minimum, but we want to know what that minimum is. In order to find that, we go back to the menu, and we are going to analyze the graph, and we are going to try to find the minimum. So now it is asking us for the lower bound. So we think that this probably is the lower bound of our search for the minimum. And now it's asking us for the upper bound. So between the lower bound and the upper bound, we are going to find a minimum. This is because some graphs actually have many local minima and maxima. So we want to specify the region within which we want to find a local min or a local max. So here it tells us that the minimum is actually at x is equal to 9, and the value for the length of the wire is 50, exactly as we had found before by doing this problem using calculus and deriving the expression and then solving for it algebraically. Thank you for joining me for the AP Calculus BC class demo. I hope to see you in class.